Hello everyone. Mihal, do you want to say some few words about Pragmadev before we start?
Well, we can. This was a work in collaboration with Airbus. We at Pragmadev deal mainly with modeling and simulation. There are two main areas of focus. It's communicating in real-time systems from one side, and from the other side something that has nothing to do with that, which is completely different, which is business processes. So we have tools that make possible the definition of business processes, verification and simulation of business processes with the aim of optimizing such business processes. So, yeah.
Great, thank you. So let's go back to the aviation world. As you might know or not know, for an airline, an aircraft generates revenue only when it's in flight. So when the aircraft is on ground, this is more of a source of cost. So the time that the aircraft spends on the ground should be minimized as much as possible. And these activities or the time that the aircraft spends on ground, we call it the turnaround operations. They are very complex operations. You might already saw some when you took a flight to go home or so. These operations are dependent on a lot of variabilities, depending on the airline, the type of airline. Is it low cost? Is it premium? The type of flight. Is it a short haul, a long haul, and so on. So a lot of variabilities, and one minor delay in one operation could lead to a whole delay in the departure. The propagation of delay is really fast, and this could lead to a lot or a huge operational cost for the airline. And this is why we need the modeling and simulation capabilities. They will help us, or trying to help us, to identify bottlenecks before they happen in real world. We try to identify what can go wrong before it happens in the real world. And then there is the optimization of the turnaround operations, the turnaround time, using the critical path analysis. And this critical path analysis helps us pinpoint the exact or the specific sequence of activities that determines the whole set or the whole time of the turnaround. To give you a context of model-based system engineering within Airbus, MVC is a major cornerstone. This is something that we highly use in the definition and development of new products within Airbus. We use a specific framework developed internally called MOFLT. It is mission, operation, functional, logical, technical. This framework helps us identify or model the whole aircraft from mission to the physical architecture of the aircraft. So we try to have this traceability from mission, operation, until the architecture within the same environment. Some issues with this kind of environment is they're using SysML modeling, which is great for depicting the operational scenarios, for depicting the architecture of the aircraft, but they lack advanced critical path analysis, which is important for the turnaround optimization. They have limited stochastic analysis. This is linked to the uncertainty of the operations, because they may vary because of an equipment that is not available or human resource that is not available, and so on. And the last thing is the limited formal verification of modeling. And this is why we started the exploration with the Pragmadev to try to find a solution for this.
So we have a problem at hand. We from our side had a solution to that problem, but there was a bridge to be built in order to actually offer the best solution to to Airbus in order to achieve what they were trying to do. So the solution in this case was to use model transformation so that we can go from the SysML models to the BPMN models. Why BPMN models? Because the tools are quite robust and have all the capabilities needed in this case. So basically BPMN plus the BPSIM notation have the possibility to come up with a model that has the functional aspect but also non-functional aspects like time, cost and resource allocations, so that then we can do a simulation of it and obtain the critical path, which was very important in this case. So basically what we tried to do is to go from the activity diagrams described in SysML and obtain a BPMN model that we can then simulate, execute and check. So I will try not to go deep in the details of the transformation. I will try to keep it high level. The basic idea, so we are trying to do some model transformation. So how we approach this? Both languages have an XML representation. So we use that the XML representation, which is very important, is standardized for both languages by the OMG. So we try to work with that XML representation to go from one language to the other. This representation basically served us for the transformation itself, but also to carry out some preliminary validation via the standardized schemas provided by the OMG. The focus in our paper and in our work was based on the case study at hand, which had many constructs used by the activity diagrams, but not everything. So we tried to focus only on those that were relevant to the case study at hand. And upon investigation, the majority of the translation rules between activity diagrams and the BPMN notation were straightforward, as you can see in the table. In the green part, are the activity diagram constructs, and in the blue side, it's the BPMN. So basically, there is a one-to-one mapping. There is an extensive also literature on the subject, but mainly focusing on the inverse, meaning that there have been some work trying to convert BPMN to SysML ID to activity diagrams. However, not everything was quite as straightforward. There are some constructs in the activity diagrams, in the SysML notation, which have not a direct mapping to the BPMN notation. So one of those is the concept of object flows in activity diagrams. So this one,
yeah, we can see it.
We cannot. No. Of course. Anyway, in the upper part of the image, the green part, there we have a very simple example of an object flow in an activity diagram. The most intuitive translation, if we wanted to go to the BPMN world, was to use the concept of the data object, because it's very similar to the concept, even semantically, of the object flow in activity diagrams. The problem with that is that in the SysML world, activity diagrams, object flows can go through different decisions, for example. So there is fork, joins, and even decisions. In the BPMN world, the only construct that can do that are the sequence flows. So basically, even if the translation was intuitive to go to the data object and data association, which is the link actually carrying the data, it was not possible to achieve what we wanted to do. So here what we tried upon investigation is that we came up with another solution, which was to use message flows. For those who know BPMN, also the message flow directly in itself, it's not a direct solution. Because even message flows cannot go through decisions or gateways, as they are called in the BPMN world. So we needed a way to model or translate the object flows into an equivalent sequence flow in the BPMN so that it can go through other more complex constructs. And this is the example how we achieve it in the picture at the bottom. So what we do is that first we model this, we translate it using message flows, which trigger start events. Triggering of the start event concept in BPMN can then trigger sequence flows. It is this part here. So basically what we do, we go from the object flow to a message flow in a start event of type message, which triggers the sequence flow, which then can go through the same type of flows that the object flow does in the activity diagrams. And then to come back to the same thing, that is the message flow, we can converge these sequence flows to end events, triggering other messages that can then generate the message flows. So via this construct or pattern, we can achieve the translation of object flows. So the idea semantically with the data association, of course they are not the same thing, but semantically they are quite similar because we get the data carrying part, which is associated to the data object, can be also associated with the message flows, because messages in BPMN also carry data. So this kind of pattern allowed us also to tackle another issue, which was call activities or call behavior actions in activity diagrams. The idea here is that for the call behavior action, we had a direct translation to call activities. The issue is with incoming and outgoing object flows. That is, a call activity, a call behavior action has a definition inside, and object flows can enter and exit this definition of the call activity. This is done in BPMN via message flows. So message flows can enter and exit call activities. So at the end, the pattern that I showed previously also addresses this issue, meaning that we take the call behavior action with incoming and outgoing object flows in the activity diagram, and then we translate it into a call activity with incoming and outgoing message flows. This is for the BPMN part. There is also the BPSIM part, which is non-functional properties of the model, which are also very important. Here we talk about time parameters, cost parameters, and also resource allocations. So what we did is that we get this information from the activity diagrams in terms of mean and max values of timing, and also the lanes that describe the resource types, and then we transform this, or we translate this into a BPSIM notation, which is it's more powerful than that, but it allows us for a first step to get information about timing and also resources. So basically at the end we have a single model that includes the functional behavior of described in the activity diagrams in the BPMN form, and also time and resource allocation requirements. So having that, now we can switch to the use case, to the real application of our solution. Please.
Thank you. So the image is blurred on purpose, but I will try to explain to you a little bit the contents of the model. So this represents, this is an activity diagram in SysML that represents a real world turnaround operation for an aircraft, an Airbus one. And the model, in the model we try to model all the complexity. So the contents, all the operations from securing the aircraft to the catering activities, pax boarding, deboarding, refueling, and so on. The variability that I talked about at the beginning of the flight, of the airline, of the placement of the flight in the airline planning. Is it first flight of the day? Is it in between flights? Is it the last flight of the day? In fact, depending on this, the sequencing or the execution of the model is different. So the complexity represented in the model, we translate it in some parametrics. So we have 33 core behavior actions, 363 distinct activities, 1060 simulation parameters, a lot of decision merge nodes, and all this was modeled in two-level modeling. So what you see here is what we call the orchestration model, but for each higher operation or turnaround operation, we modeled it a little bit into details to understand more how the equipment interacts with the aircraft and so on. So let's see how the model transformation was done. As I said, the SysML model or the operational scenario was done with an activity diagram. It was hosted in Cameo Systems Modeler. Thanks to the solution developed by Pragmadev, the AD2BP solution to transform the SysML to BPMN through an XML export. We retrieved the scenario in Pragmadev process as BPMN modeled, with no changing of the content of the model, which is great, and this is what we were looking for. And then before looking at the simulation, we had to make sure that our model was functional and was deadlock-free. This is some of the capabilities that Pragmadev give us, or allowed us to have, is the formal verification capability. So we thought our model was perfect on paper, but by transforming it using the tool, we found 16 deadlocks. And this 16 deadlocks, would have invalidated our simulation results. So within the tool, we had the opportunity to find the blocking state and see where is the source of blocking and do the modification, either directly on the tool or go back in our SysML model, do the modification, export, do the transformation, and then rerun the simulation, which was fairly quick. Then the second topic, or the second capability that we were looking for, was the critical path identification. This is something as well that we could have retrieved within the tool. So the simulation and the identification of the critical path was done in less than a minute. And I can remind you of the complexity and the number of the artifacts that were in the model, so it was great to see. And the last capability that we were looking for was the calculation of the overall turnaround time. Here we have 42 minutes, which for a low-cost company wouldn't be acceptable at all, because it's more than 30 minutes. So this is something that we can see and think how to optimize, what kind of activities that we can change, and so on. So I think we are on time to conclude. So we can see, we can say that we have successfully obtained a structured transformation framework from SysML activity diagrams to BPMN models. We had the advanced simulation with the formal verification of our models through the deadlock detections. However, we still have some limitation within this exploration. So it is valid on one representative case study, which is the turnaround operation. But the aircraft operations are not only turnaround operations. There are flights, there are maintenance, there are cockpits, and so on. So the idea or the objective then to continue the exploration, to extend this analysis to other phases or other cross-operational phases by integrating state machine. It's another diagram within SysML. Extend the analysis to resource management, because this is something we talked about, but we didn't test yet. And the last thing is have advanced visualization. And this is something we need to better interpret or understand the simulation results, like gunshots, for example. And this is it for us.
Yeah.
You have some question?